Hi everyone, welcome to the online causal inference seminar. Today we are glad to welcome two researchers, Michael Celentano from UC Berkeley and Chris Harshall joined from UC Berkeley and MIT to give two amazing talks. So Michael will go first, and today the Q&A will be handled by Emma. So I'll switch to Emma.
Hi all, so welcome again. Today these two talks are 30 minutes each. That kind of includes more or less the questions. So please submit your questions as soon as they come up to the Q&A, and I will bring them up to the speakers. So thank you all, and I think Michael, take it away.
Okay, great, thanks. So let's see. Is that working?
Works
Good.
great.
All right, cool. So thanks for having me. It's good to be back. I actually used to be one of the organizers of this seminar, but I never had the opportunity to give a talk. So very excited to be back. So today I'm going to be talking about some work I recently finished with Martin Wainwright on estimating a population mean with missing data, or equivalently, if you're into causal inference, which you may be if you're here. Estimating something like the expected mean of a treated potential outcome when not everyone in the population receives treatment. And what's going to distinguish this talk is that certain nuisance parameters that are usually required to be estimated consistently to estimate the population mean will be sort of fundamentally impossible to estimate consistently. And so we're going to have to develop some new methodology, at least within the confines of the particular model that I study today. It's a pretty theoretical talk, so I've done my best to explain as much as I can with figures and plots rather than formulas, and so hopefully that's effective. The paper is on arXiv, and you can find it here. So, okay, so let me just set up the problem and the model. So we study a linear model. So each member of the population has an outcome y. That's some noisy linear function of some high dimensional features x. So I have p high dimensional features x, and we're going to consider that they're Gaussian. And the expected value of the outcome given the features is going to be denoted by mu of x, which is just a linear function of x. And on the left, I've plotted data from this model. So I have 5,000 samples, so pretty large sample size and a very large dimensionality. So I have 6,250 features, and it's a pretty sparse model. So only 30 of the coordinates of my linear model parameter are non-zero. And for each member of the population, on the x-axis, I've plotted mu of x, or this linear function of x. So this is the expected value of y given x. And on the y-axis, I've plotted the outcome. Okay, and so in this model, the features are pretty predictive of the outcome, but they're not completely predictive. And we want to estimate the expected value of y. So this histogram is a histogram of the outcome values. And there's actually two dotted lines plotted here that you can't distinguish because they're right on top of each other. One is in gray, which is the population mean, which is 0 in this example, and that will be the population mean throughout the talk. And then in blue is the empirical mean in this data, which is very, very close to the population mean. Now, of course, we're going to assume there's some missing outcome data. So this color now indicates whether the member of the population has an outcome that is observed by the statistician. Green means that they do, and red means that they do not. And that missingness is going to be determined by a GLM, which you can just imagine is logistic regression, though we don't require it to be. And in the model I've simulated from, we see there's some confounding. So the missingness is correlated with the value of the outcome. And so if I just take the mean of the outcomes among those members of my population that have an observed outcome, it's biased upwards for the population mean. Okay, so one way to estimate the population mean in this problem, which I think many or all of you are familiar with, is outcome imputation. So what I've done here is I have some training data, which is independent of the data that I've plotted here, and which is of the same size. So I have 5,000 training samples from this distribution. And I used that data to fit the lasso to get an estimate of my linear model parameter. And I used that estimate to impute the expected value of y given x on the members in the population that I've plotted here. So now the y-axis is not the outcome, it's the mu hat of x, the imputed outcome. And because the sparsity is, it's pretty sparse and the sample size is pretty large, the lasso does very well. So we see that it almost perfectly recovers, not exactly perfectly, but pretty close to perfectly recovers the true value of mu of x. And because I can impute mu hat of x for all members of my sample, if I average over mu hat of x, I get in blue here an estimate that's very close to the true population mean. And in green, I have the empirical average of mu hat of x over the members of my population with observed outcomes, in red over members of my population with unobserved outcomes. But what's important here is in blue, which is the average over the entire population. Okay, so that was a very sparse setting, but what we're going to be sort of focused on in this talk is settings where there's much less structure. Okay, so if I have a much sort of more complicated parameter, so now 1500 of the coordinates of my parameter are non-zero, when I fit the lasso on my training data, I get a much less accurate estimate of the outcome model, right? So the mu hat of x is now very far from mu of x on average. It's still correlated with mu of x, but it's not lying anywhere close to this y equals x line. And as a result, because there's some bias in the lasso estimate, if I average over mu hat of x on my sample, I get biased and inconsistent estimates of the population mean. So the blue line here is sort of upward biased for the population mean, as are the means of mu hat of x over both the members of my population with observed outcomes and unobserved outcomes. Okay, so what this talk is about is how do I estimate the population mean when I have an inaccurate estimate of this nuisance parameter mu of x. Now, of course, there's other approaches to estimating population means that many of you or all of you are familiar with. On the other side of the spectrum, we have inverse propensity weighting, which requires that you have an estimate of your propensity score, and it will provide a consistent estimate of your population mean if the propensity score is consistent. And AIPW combines outcome imputation and IPW. It starts with sort of the outcome imputation estimator and then adds a correction term, and it satisfies this double robustness property that it will be consistent for the population mean, provided either the outcome model or the propensity model are estimated consistently. Okay, so really the regime I'm going to look at is a regime where neither of these things can be estimated consistently. So both the outcome and the propensity models are inaccurate. And the reason they're inaccurate is that they're sort of, it's not because they are misspecified. It's because they're just sort of too complex and we don't have enough samples to estimate them well. So I'm going to consider cases where their dimensionality and really their intrinsic dimensionality is on the same order as the sample size. Okay. So formally, the model we consider is what I've already stated. So it's a linear outcome model and some high dimensional features, and a GLM propensity model, which we can imagine is logistic regression, say. And I'm going to study this model in a certain high dimensional limit in which I allow the dimensionality and the sample size to grow simultaneously, and they grow in such a way that asymptotically their ratio is of order 1. Okay. Now, getting into the mathematical details can get very complicated, and keeping track of these high dimensional limits can be sort of complicated. So really what you should try to keep in mind is that really what I'm studying is the left plot and not the right plot. So if you look at, semi-parametrics and in particular sort of high dimensional nuisance parameters, often they're studied in high dimensional limits in which, asymptotically the outcome model or the propensity model is consistent for the true outcome or propensity model. And so in those limits, you're basically studying situations where if you were to run your simulation, you should expect to get a plot that looks like this. Whereas in my limit, in this proportional asymptotics, you should get plots that look like this, and you should continue to get plots that look like this even as you take the limit. So this sort of noisiness of this plot will be retained even as I take n and p to be arbitrarily large in the high dimensional limit I've chosen. Okay, so that's the setup. Now let me just sort of tell you a bit about some prior work that will set the stage for the results that I present. And so what's previously been studied is the case that n is bigger than p in an inconsistency regime, in a setting in which both the outcome and the propensity models cannot be estimated consistently. Okay, and in this setting, it's actually not that difficult to get a consistent estimate of the population mean. You can just use OLS, and in particular, you can use OLS as a plugin to either outcome imputation or AIPW. So Yadlowski studied this in 2022, and he showed that these approaches are root n consistent for the population mean, even though the outcome model and the propensity model are not consistent. And then Jiang, Mukherjee, Sen, and Sur showed that AIPW is not only root n consistent, but it's asymptotically normal and unbiased, and they quantified its variance. And both of these works showed that these estimates experience a variance inflation relative to what you would sort of get in the consistency regime. So relative to what you would get if you estimated your nuisance parameters consistently. And in particular for AIPW, you have a variance inflation relative to the classical semi-parametric efficiency lower bound. Okay, so here's a simulation that just sort of recapitulates these results, and I'm going to show plots like this later for the results that we present. So hopefully this will get us used to looking at these types of plots. And so what I've done here is on the x-axis, I've plotted the sample size, and in each sample size, I've considered a model in which the dimensionality is 7% of n. So it's proportional to n, but it's also quite a bit less than n, but it's proportional to n. So this is a proportional asymptotics. And in red, I've computed an estimate of the population mean, which in this case is 0, using outcome imputation. In green, I've plotted the mean of my estimate when I use AIPW, and in blue, I've plotted the mean of my estimate when I use IPW. And on right, I've done the same thing across sample sizes n, but I've computed the variance of my estimate in my simulations. And so on the left, we see that both outcome imputation and AIPW, in keeping with these prior works, appears to be there's no apparent bias, whereas IPW is not even consistent, so it has an enormous bias, and it has a bias that in particular does not decay or appear to decay as my sample size grows. On the right, we see that the variance of all the estimators decays like 1 over n, which indicates that, at least provided the bias is appropriately controlled, that these things are root n consistent, although IPW is not consistent at all, but outcome imputation and AIPW are. Okay, so how is this possible? So I think the intuition for why this happens is going to be sort of a centerpiece for the talk. So why can outcome imputation be consistent for the population mean when the outcome model is itself inconsistent? And the reason is that OLS is unbiased. Okay, so here if I plot mu hat x on the y-axis and mu of x on the x-axis, when I have sort of a dimensionality that is smaller than n, but not, vanishingly small relative to n, I see that I don't have points that are really right on top of the y equals x line, but they are centered around the y equals x line. And so when I average over mu hat of x, I get that sort of those deviations from the y equals x line cancel out, and I get in blue here a consistent estimate of my population mean. And this type of phenomenon is sort of common in semi-parametrics, that if you're estimating a nuisance parameter, you really want to undersmooth. You care more about having low bias in a nuisance parameter estimate than low variance. And when you use OLS, this is sort of taking that to the extreme where you have, literally no bias, and you have, variance of order 1. Okay, so what we studied is a case where n is less than p, and so now OLS is not possible, right? So I don't have access to this estimator that allowed me to have outcome imputation succeed despite the inconsistency of my nuisance parameters. And so is there a way to successfully estimate the population mean in this setting? And the answer is yes. And perhaps based on the intuition I've sort of stated so far, it's not so surprising that what you need to do is find some way to estimate, to get something like an unbiased estimate of your parameter. Okay, but because n is less than p, it's hard to get unbiased estimates of your parameter. You're required to use some regularization in estimating your parameter. And so what we plug in is a debiased version of a regularized estimator. Okay, and we draw on sort of a large literature on debiasing estimators like the lasso and ridge. This is sort of a very incomplete list of references. This is a very large literature, but these references in particular look at cases where you're sort of debiasing regularized estimates in what I would call an inconsistency regime, which is the regime we're in. Okay, so I'm going to explain to you what this debiased estimate is, but before I do that, let me just sort of convince you that it works in simulation. So here in red, I've plotted the same plot, except now rather than have p equal 7% of n, p is dramatically larger. It's 1.25 n. And I've used this debiased plugin, and we see that across sample sizes, it doesn't have any sort of apparent bias for the true population mean, and it also appears to have a variance that decays as 1/n. So what we're going to show in this paper is just the consistency of this estimate. We're not going to sort of give a rate on this variance decay, though it does appear that our estimate achieves a variance decay of 1/n. But that's something that we haven't been able to prove. Okay, and so let me just show you another plot to show you how our estimator performs. So this plot I already showed you. So this is how things look when I use just the lasso, the vanilla lasso, as a plugin for my outcome model, and it has some upward bias that gives an inconsistent estimate of the population mean. Whereas if I use this sort of debiased lasso plugin according to the construction we present in our paper, we get a much noisier estimate of mu hat of x, but it's sort of centered on the line y equals x. And that means that the population mean returns to its correct value at 0. Okay, so here's our theorem. Okay, so our theorem has a lot of technical assumptions. I won't list all of them here, but I'm going to list the ones that I think are the most important. So first, we have to make an assumption about that places us in this inconsistency regime. So in particular, as I've already said, we're going to assume that the sample size and the dimensionality of the parameters are of order 1, of the same order. And we're going to make some structural assumptions about our outcome and our propensity models, but we're not going to make so many structural assumptions that it becomes possible to estimate these parameters well. So in particular, the only thing we assume is some L2, bound on the model parameters, which basically just says that the signal to noise ratio in these models is not perfect. Okay, so it means that the features are not perfectly predictive of the outcome or perfectly predictive of the treatment assignment. So the second of these you can think of as sort of an overlap type assumption. Okay, so we're going to require that we use a particular plugin. So as I've sort of argued already, the choice of plugin is very important here. We can't just use any old plugin to our outcome imputation. And so we're going to require a certain debiasing construction that, if I have time, I'll tell you a bit about in a few slides. And it is you debias a certain base estimator. In our case, we consider ridge regression and sort of similar penalties. We don't actually have a theorem about the lasso. I believe, I believe not only is it the theorem true for the lasso, and it's, possible with enough effort to prove for the lasso. But it was already hard enough to do this theory for ridge, and so that's where we started, even though I think lasso is a much more compelling example than ridge. Okay, and we're going to make admittedly strong assumptions about our features. So they're going to be Gaussian, and they're going to have a well-conditioned covariance. Okay, now this Gaussian assumption appears very frequently in this literature. It's not, it's likely not essential. Really, the results should hold for a much larger class of features that have, sufficiently light tails, for example. But as a starting point and as a tool for identifying good methodology that we can then try to extend to weaker assumptions, we're just going to start with this Gaussian assumption. Okay, so under these assumptions and then a bunch of technical conditions that you can find in the paper, if you take any limit that respects these assumptions, the estimate of your population mean using this outcome imputation with the debiased plugin will be consistent for the population mean. And we don't provide any sort of rate for this, though I sort of think it's probably a root n rate. Okay, so let me tell you how this debiasing works. Okay, so there's a large literature on debiasing. And the way these estimates work is you start with a base estimate like ridge or lasso, and then you add some adjustment term to debias it. So it's actually related to AIPW, which also has this structure. Okay, so here's my base estimate. Let's say it came from ridge. And then my debiasing adjustment is sort of complicated. Okay, so it's sort of the residuals multiplied by X transpose. And then I have some inverse of my feature covariance. And then this is some adjustment factor that is empirical, but that I don't want to describe. It's related to sort of the degrees of freedom of the estimator. Okay. Now, usually in the debiasing literature, this is the unconditional feature covariance, or a very good estimate of it. And we're going to have to sort of modify existing theory, because if you think about it, the estimate theta hat was not fit using all of our observations. It was only fit using the observations that had an outcome observed. And so that means that really what we should use here is not the inverse of the feature covariance, but rather the inverse of the feature covariance conditional on the outcome having been observed. Okay. And in particular, this object depends on the propensity model, because the conditional distribution of the features, conditional on observing an outcome, is related to the propensity model. Okay. So for example, if the variance of X of the features is the identity covariance, that means that all the features are independent, then this is sort of the form that the conditional covariance of the features takes. It's the unconditional covariance plus some rank 1 update related to the propensity model parameter. And so while the estimator appeared to only involve outcome modeling to begin with, it turns out that to do this debiasing of the outcome model, I need to do some propensity modeling. And this is what distinguishes it, or one of the things that distinguishes it from the case n bigger than p when we use OLS, and we don't have to worry about the propensity model at all. And the challenge we have here is that just as the outcome model is inconsistent, the propensity model is inconsistent. And so we can't just use a plugin estimate for the propensity model here to carry out this debiasing and expect it to be successful. And indeed, if we just use a naive plugin, this will not successfully debias our outcome model. So what we do is we have to be very careful about how we incorporate a plugin estimate into this debiasing procedure, just as we had to be very careful about how we incorporated an outcome model estimate into our outcome imputation. And this T somehow went downstairs, but it's supposed to be upstairs. This is a transpose. Okay, so what we do is we have to actually get a debias estimate also of the propensity model. And then there's going to be some issues still, because there's these debiased estimates are correlated with your data in a complicated way, and so this estimate is going to still be biased, and so then we have to add some adjustment term, which is very complicated to write on a slide, so I haven't done it, but that will sort of correct this bias. Okay, so this is maybe just a preview of what the full estimator looks like, and if you're interested, you can look at the paper. Okay, now I think I'm running a little low on time, so I'm going to maybe try to finish up in 2 minutes. Well, maybe I'll skip this section because I think I'm running out of time. But what I just wanted to emphasize in this section is that the propensity model here plays a central role, as I just described. As I said, when n is bigger than p, we don't have to worry about the propensity model at all. We can just use OLS. Whereas when n is less than p, we do have to sort of use the propensity model to carry out this debiasing construction. But the reason we're using it is somehow very different. We're not using it to do some reweighting of our sample the way we would with IPW or AIPW. We're using it to debias the outcome model as an input into outcome imputation. So it's sort of a new role, but still a very essential and central role for the propensity model. And I don't, know if there's a way in this sort of inconsistency regime to achieve an unbiased estimate of the outcome population mean without using some sort of propensity model despite its inconsistency. Okay, so let me just then skip all this stuff because I don't have time and just jump forward to my conclusion. Okay, so what did I tell you about today? So I told you about consistent estimation of the population mean in an inconsistency regime in which n is less than p. I should be transparent about what I think the shortcomings of these results are. So admittedly, I've sort of studied a very stylized model, perhaps by necessity. So if I had a fully non-parametric model, then there are lower bounds that show that you cannot hope to achieve consistency in general without having consistent estimates of at least your outcome model or at least your propensity model. So really what this talk is about, okay, within the confines of some certain types of assumptions, can we get consistency for our population mean through some other means than consistency of one of your nuisance parameters? And here we've shown that the answer is yes, when you have sort of a linear GLM with some sort of random feature assumption, which can be relaxed. Okay. So despite these shortcomings, I think, what we've done by studying this sort of admittedly stylized model is we've discovered some methodology and shown that it works. That methodology is to use the debias ridge and lasso as an imputation for your outcome and outcome imputation. And that we've shown that actually you can use the propensity model to achieve that debiasing. And so even though we've sort of developed this method in the confines of a stylized model, I sort of wonder whether this general strategy is useful quite broadly, that when you're doing sort of semi-parametrics and you're fitting models with the lasso, perhaps rather than input the lasso estimate directly into outcome computation, you can draw on either the debiasing procedure we have presented or other debiasing procedures to first debias those estimates and then use those as inputs, and whether that will lead to more robust, and accurate estimates in practice. So that's all I have to say. Thanks for listening. I think I'm maybe got 1 minute or two for questions. I'll stop there.
Thank you, Michael. There are indeed 2 questions for you in the Q&A,
Okay.
and if people keep asking questions, I'm sure you can answer later on. You can even type. But okay, for now, there's a question from Sean Seaman. When you say that you can use OLS when n is bigger than p, I presume that the expectation of y given x must be linear in x. Is that right?
Yeah. So all these works depend very sensitively on correct model specification. So I think, yeah, I mean, the short answer is yes. I think, I think that when you are in high dimensions and estimation gets harder, you start to have to lean more heavily on sort of model specification. So this is linear models, yeah.
I guess another short, maybe not, question: how would you address the problem of non-Gaussianity?
So we don't address it in our paper, but I think that it should be possible to address, and there's papers in this literature that study universality and try to generalize the results that are proven for Gaussian distributions to non-Gaussian distributions. I have no reason to, I have reason to be hopeful that such generalizations are possible here, but I don't know that that's open.
And there was a follow-up: to which extent does the chosen regularization method affect your derivations?
Yeah, so we consider basically a class of penalties that is strongly convex and smooth. And so the construction is very general, though if you think of which popular penalties are strongly convex and smooth, I think ridge is the primary example. That being said, it's really a question of difficulty in the proofs. It's not a question of difficulty in writing down and being able to implement your estimator. So if you give me sort of any convex regularization, I can pretty readily, write down what I think the correct debiasing method is. I can run simulations with it. It's just that in order for the proofs to go through, you need, or at least the current proof that we did, which was already quite involved, requires drawing on some regularity of those penalties. So I think, yeah, I think, I think constructing the debias estimate is sort of something we know how to do for a general penalty, but the proofs are still restricted to penalties that satisfy some regularity.
All right, great. Thank you. Thank you so much. There's more questions, but we are out of time. So we'll move on to Chris, and Michael, feel free to keep chatting about the question.